Welcome to Standex Electronics presentation on magnetic mapping and how it can help the reed sensor designer. Essentially, magnetic mapping is a tool to allow the designer an inside look when designing a reed sensor into a given application. We all know we cannot see a magnetic field. However, we can see and feel its effects. By examining the effects from a magnetic field, we are able to present what a given magnetic field looks like using magnetic mapping technology. We will define all its key functions and key terms. We will investigate how the reed sensors can be better designed using the mapping technology. To fully understand the concept of magnetic mapping, you need to fully understand the basic function of a reed sensor. The reed sensor is an ideal method of sensing and detecting movement of any kind. Typically, a permanent magnet is mounted to a moving member. This can be a piston, a float, a rotating disc, and many more. The reed sensor houses a hermetically sealed reed switch that is generally mounted to a printed circuit board or hardwired to an electrical circuit. The reed switch senses the physical movement of the magnet, and the reed contacts will close or open depending upon whether the magnet is moving toward the reed sensor or away from it. As described, the key function of a reed sensor is to close and open in the presence of a magnetic field. When a reed sensor's contacts close, that is described as its pull-in or closure point. Conversely, when the reed sensor's contacts open, that is said to be its dropout or opening point. Reed sensor hysteresis is defined as the ratio of the dropout pull-in. Understanding hysteresis in a reed sensor is very important, particularly in liquid level sensing. Many level sensing applications are in moving vehicles where fuel, oil, brake fluid, wiper fluid, and more are monitored. Many of these applications activate a light on the dashboard. Without any hysteresis in the reed sensor, the lights once activated would continue to blink on with every bump in the road and on every turn. Reed sensors can be selected for varying percentages of hysteresis. Generally, a wide differential, one ideally used in liquid level sensing, is about a 50% differential. For example, in a given application, if the closure point is 1 inch from a given reference point, the dropout point will be 0.5 inches. Or hysteresis equals dropout pull-in times 100% equals 0.5 over 1.0 times 100% equals 50%. The magnetic fields we will be talking about are generally produced by permanent magnets, and we will be working with ferromagnetic materials. These materials influence the flow of the magnetic lines of force. Typically, ferromagnetic materials are generally iron, steel, nickel, and cobalt. To accomplish and define the magnetic mapping points, we will be holding the reed sensor fixed while moving the magnet incrementally and measuring its pull-in and dropout points. The incremental measurements must be carried out in all 3 dimensions. A software program is then used to bridge the entire 3-dimensional magnetic structure. The best way to understand magnetic mapping and its results is to see it. The following video shows the magnetic spheres of influence and how the magnet and reed sensor interact. These invisible boundaries are real and can only be attained by gathering the data points through incrementally mapping the boundaries. The basic boundary points for the pull-in and dropout fields can clearly show how they are portrayed in 3 dimensions. Here the pull-in and dropout boundaries are shown in a frontal view, with the magnet shown above these lobes. The contacts are open in the sensor below on the PCB. If the magnet were to move vertically downward and enter the purple pull-in boundary, the contacts will close. As long as the magnet stays inside the purple boundary, the contacts will stay closed. If the magnet is withdrawn, moving vertically upwards, The contacts will open once the magnet reaches the end or top of the light orange boundary. As shown, the hysteresis is the spatial distance shown between the pull-in and drop-out lobes. This is the physical distance the magnet must travel when going from the on state to the off state. Here the pull-in and drop-out boundaries are shown from the side view. With magnets shown above these lobes, the contacts are open in the sensor below on the PCB. What is immediately obvious is that you can clearly see that the magnet is offset from the reed sensor. What becomes clear in this case is that the magnet must travel further down to reach the pull-in boundary before the contacts will close. If the designer is looking for the shortest distance to travel, then this is not an ideal design. Either the magnet must be shifted directly over the reed sensor for its vertical movement, or the reed sensor must be moved on the PCB to be directly under the vertical movement of the magnet. In either case, the designer will enjoy the shortest possible magnet downward movement to close the contacts. As shown, the hysteresis is the spatial distance shown between the pull-in and drop-out lobes directly under where the magnet makes its descent. This again is the physical distance the magnet must travel when going from the on state to the off state. In the previous example, the mapped boundaries for the pull-in and drop-out are clearly shown. Also, it becomes clear just how important three-dimensional viewing is. As you will note from the frontal view, everything looked fine. However, when we went to the side view, it became very clear that the misalignment of the magnet and the reed sensor would affect the operate and release points of the reed sensor. So you can see from this example how the three-dimensional pull-in and drop-out boundaries can play an important part for proper design and optimal parameter functioning. In the simple example we have just looked at, important information is immediately gained from the boundary portrayals. Furthermore, if the designer is looking for maximum sensitivity, the designer must change the design. The end view clearly indicates the lack of sensitivity because the magnet has to travel further vertically downward. If the positions of the magnet and reed sensor cannot be moved because of design or operating constraints, the sensitivity of the reed sensor can be increased, which in turn shorten the magnet travel distance to close the contacts. The other option would be to use a stronger magnet. This will usually add to the component cost. The end view clearly indicates the lack of sensitivity because the magnet has to travel further vertically downward. In the example we have previously presented, it's obvious where the issues are in the existing design. Most of the time, the design parameters are a lot more complicated. When you begin adding other magnets, sensors, or any ferromagnetic materials, the simple lobe boundaries we have mapped out are altered dramatically. The mapping then takes on an entirely new look where boundary definitions may be filled with subtle twists and turns in the pull-in and drop-out boundaries. So the mapping clearly provides pull-in and drop-out fields. They allow the designer to properly position the magnets and reed sensors in their ideal positions, thus providing the designer a solidified design before finalizing all design constraints. Magnetically mapping allows the designer to adequately choose the correct operate and deactivate points. It allows the designer a visual representation that his design is operating well within the magnetic envelopes, avoiding any potential issues. The natural hysteresis of the reed sensor is clearly shown delineating this important zone, and the reed sensor and magnet cost can then be optimized.